just in case no one notices, I did finally, about 3 minutes ago, get the homework assignment that's due on Wednesday posted on Moodle. I try to give you more time than that. I try to give you Sunday, Monday, Tuesday, Wednesday. You just have the rest of Monday, Tuesday, Wednesday. There's 12 questions, like per normal. One thing as I was going through that I think I just missed it when I was going through my slides, was another important thing about the solar nebula theory. And that is why there is a difference between the terrestrial planets and the Jovian planets. Now, just to make sure that we're all up to speed, let us name the planets in order from the sun out. So here's the sun. Sun. What's the first planet closest to the sun? Mercury, then? Venus. Then the third rock from the sun? Yeah. Fourth one? Next? 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 Uranus, and finally Neptune. Okay, now where's the division between the types? What do we have in that division? Okay, there's the asteroid belt. Is there a special reason for the asteroid belt being there? There are a lot of theories that go both ways on that question. Some people say, yes, it's, a region where it's not stable for a planet to form because the gravity of Jupiter is too strong and Jupiter would shred a planet if it was in that region. And so that this must be the result of something that was trying to form there that Jupiter shredded. We'll learn later more about the asteroid belt, but that's one explanation of why we have a bunch of asteroids there. There is a significant difference between the planets that are closer than the asteroid belt and the planets that are farther. And the asteroid belt is not important to this discussion, other than it just serves as a nice convenient divider. The ones that are closer than the asteroid belt are all rocks. The ones that are farther have gas. And the question is why? And in answering that question, one of the things that scientists have noted is that the things that the rocky planets are made up of are things that have very high melting temperatures. Things like iron and silicates, silicon and oxygen compounds. And so looking at that, scientists have come to a conclusion that we have this thing that's called the frost line. And so the frost line is another thing that during the planet formation period was between Mars and Jupiter. The frost line is the line that separates where the temperatures were cool enough for things that we normally think of as gases and liquids to stick together. At high temperatures, water will stick together and get liquid at low temperature. At high temperature, it turns into a gas. Well, the frost line is basically where most things will be condensed. If you're closer than that, they're going to be gases. If they're farther than that, they're going to be condensed. Why is that important? In the early stages of planet formation, if you're beyond the frost line, you could have molecules of things like water or methane come together and stick together. But if you're closer than the frost line, they won't. They just come together, they'll bounce off of each other. They have too much kinetic energy. You're going too fast because temperature is a measurement of how fast you're traveling, the kinetic energy, and they won't stick together. So things that are closer than the frost line, it was too hot for them to stick together. Only things that had high melting temperatures could stick together. And thus the planets were composed of only those things with high melting temperature. So inside of the frost line, you have high melting point materials. Things like the silicon dioxide or iron, etc. Those are by far the predominant things. Beyond, I didn't mean to do that. Beyond the frost line, you have anything could stick together. So what does that mean? You have the same type of material spread out everywhere, but beyond the frost line, you can capture everything. Inside, you can't. Hence, the amount of material you can capture for a planet outside of the frost line is much more material. So they're going to grow more rapidly. Now, once they get to be large mass, you can hold on to anything, right? The Earth has an atmosphere. We can hold on to anything except for hydrogen and helium because we have enough mass now. But before you have enough mass, you can't hold on to them. And so these were able to accumulate lots of things that we would consider gases and liquids early on, grew very big. They still collected the high temperature melting point stuff, right? There's nothing barring that. And so that's why they have the rocks in the center, because they collected the high temperature melting stuff, but then they collected the stuff we call volatiles, which is what gives them their outer atmospheres of gas and then liquid layer, be it liquid hydrogen or water, so you get later in the bigger ones. So that's believed to be why we have significantly different types of plants depending on where they formed. Okay, you've seen the slide on convection as well as the next one, just getting us back into the mood of where we left off. So we talked about the rifting, right? And how we have oceans that are having the floor expand, and then when that ocean floor meets the continental crust, because the ocean floor is basalt, a dense material, and the continental material is less dense, the ocean one slides under, we call it subduction, which creates a lot of grinding, hence volcanoes. Also creates a lot of stress, hence a lot of earthquakes. So you have earthquakes and volcanoes at these boundaries where the subduction occurs. And remember, we have these convection currents that's effectively driving the whole thing. So two places where you're likely to find volcanoes are at the mid-ocean rifts, where you're forming a gap and having hot magma push up, and at the subduction zones where the ocean meets the land. So I'm from California. California, the ocean meets the land. California, we have lots of volcanoes. They're all dormant now. Yeah, good stuff. We also have a fair number of earthquakes because of this. Now, why are they dormant now? If they're dormant now, that would suggest that maybe we're not doing much grinding now. And that's indeed the case. Right now, the ocean plate is not sliding underneath. The Pacific plate is not sliding underneath the North American plate. Instead, they're sliding like this. It's called strike slip. And hence you've heard things like someday Los Angeles will be next to San Francisco. It's because Los Angeles is, I believe, on the ocean side of the boundary. And so that northern slide means that Los Angeles is sliding north compared to the continent. And, give us a few million years of travel at, an inch a year, whatever it is. Eventually that could happen. And when you have a big earthquake, it might jump 10 meters, which is pretty significant, right? At this point, you guys were toddlers and don't even remember. There was a huge earthquake in Indonesia, caused massive tsunamis around 2005, 2006. And if I remember right, the ocean floor shifted by 10 meters vertically.
Wait, what was this again?
An earthquake in Indonesia. If I remember right, it was 10 meters vertically, which is a huge shift. And what happens? All that water gets lifted up, and then what does it do? Flows out, sends out a wave through the ocean. We call those tsunamis, which is Japanese for a harbor wave. Why are they called harbor waves? Because as it's going through the ocean, you don't really notice it. If you're flying overhead, you might see it looks like there's a shadow on the ocean because all the water is being compressed, so all of the little waves in the ocean get closer together, which makes the light go more to the sides. But when it gets to shallow water, then it stacks up because all the energy goes vertical when you get shallow water. And then you have a big wall of water that just keeps going because behind the tsunami, all of the water is moving. So it's not like a normal wave when it gets to shore, it just goes up and comes down. You have more water pushing behind it, so it just keeps going. So that's, big waves are not the same as tsunamis because big wave will stop, whereas the tsunami keeps going a lot more. Okay, that was, of course, not what I intended to talk about here, but we got it. Finally, this is the last slide we had from last lecture. We talked about the plate boundaries and seeing the magnetic fields that alternate and are symmetric across the rift zones, adding, that would be predicted by the idea of the rift zones being pushed apart. It gives us no reason to believe it. Over on the right, you see a diagram showing the major tectonic plates. The tectonic plates are the pieces of the Earth that are sliding around. This idea is only about 100 years old. That's what Alfred Wegener came up with the idea, and he came up with it the same way I did. Okay, I've got to tell you, this is all tongue-in-cheek, bona fide genius. When I was a kid reading the World Book Encyclopedia, I noticed, man, South America totally looks like it would fit into Africa. I mean, it does, right? And I was like, it must have been that these used to be together. Well, that's what Wegener came up with, obviously 60 years, 50 years, whatever, before I came up with it. And people said, you're crazy, dude. How would the planets move? Not the planets, excuse me. The planets. How would the continents move? Well, now we have a good understanding of how this moves. We call this whole process plate tectonics, and you can think of these plates as like the shell of an egg. You take that egg, you hard boil it, you drop it on the desk, and the shell fractures into a bunch of pieces. That's basically what we have, is we have the surface of our ball has a bunch of cracks on it. And then you have forces that are pushing those cracks so they slide. And of course, unlike the egg, you'll form new shell where it slides around. And so this is showing the major cracks. These things here are the rift zones. And then you have subduction zones. So you have the plate boundaries. So this here, here's our Pacific plate. And you have the Nazca plate. Nazca plate, I think, is the most active plate, which makes living in Chile your most exciting spot on Earth for earthquakes. And you can see earthquakes I think these are earthquakes that are marked in red. It doesn't have a thing there, but I think those are earthquakes marked in red so you can see where they are. Earthquake, oh shoot. I was trying to zoom in, failed. Come to me. Uh-oh. Oh, it's over here on the right. That's not it. It never works the way I want it to. Forget it. We'll not try to zoom in today. The Ring of Fire. You guys heard the Ring of Fire? And nothing to do with a song. The Ring of Fire is the ring around the Pacific Plate. And it's called the Ring of Fire because you have volcanoes all around the Pacific Plate boundaries because of the sliding of the plate. Okay, let's move forward. These plates have moved over time. We have here some rudimentary pictures. I'm going to spend, I kid you not, 5 to 10 minutes of our valuable class time, hopefully, playing this. I should have opened. Okay, I think it's opening now. Yes, playing this YouTube video. And let me turn off the sound. I got annoyed with the sound about 7 seconds in. Sound off. Come on, full screen. One of these buttons is going to make it go full screen, trust me. Okay, it's gone full screen. Do you see that? Yeah, you do. Okay. Oh,
You pushed it all the way to the
apparently I did.
Wow.
I'm doing really well. Okay, this is about the beginning. Well, not quite. That is the beginning. Okay, I want you to notice the time here. MYR is million years. So that's 2.853 billion years ago is what it's showing. This is showing what we believe, based on looking at the magnetic information stored in rocks, the surface of the Earth look like. Now, you'll notice that there's more parts underwater, sometimes less parts underwater, sometimes. Has to do both with the temperatures on Earth, meaning you're going to have higher or lower water levels, as well as the understanding of elevations back then. So right now, we notice the supercontinent. We just finished the supercontinent Antarctica. It's gone now. There's no supercontinent. So Antarctica, I think, is the earliest supercontinent, where you had a bunch of land mass all together in one spot. And we're going to come through a lot of supercontinents here as it progresses. Right now, looks pretty random. See stuff coming together down there at the bottom. And Atlantica. Now you see that it has things labeled. So that mass that's Atlantica is what's going to become Africa eventually. Part of it. There's part of Africa there too.
What the?
You see Australia all over the place.
Why is it moving faster on this side?
Honestly, I don't know. Okay, now we have Colombia.
Hey!
And see, we've got there a little bit of North America up here. A lot of Africa still, a lot of Australia. Or actually, that's mostly Eurasia. Australia is this stuff here.
Is yellow South America?
What was that?
Is yellow South America?
Yeah, yellow South America. It's hard to read the color scale here, but that's... Okay, Colombia is going to break apart. We're eventually going to get to one you recognize. And here we have Rodinia. Pretty big landmass. Notice this is 1 million years ago now. Anybody know when life is believed to have started? That is, let's go with the Cambrian explosion, when we have the first proliferation of different kinds of fossils. It's 540 million years ago, roughly. So we're getting close to the time when the first major fossil proliferation begins. Now we're in Panotia, or something like that. Panotia? I don't know. So Gondwana. Gondwana is when the Cambrian explosion occurs, when you had Gondwana going on. And what's going to come after Gondwana? Pangea. Most people have heard of Pangea. Some people call this Pangea theory. Now you can start seeing things, right? You see Africa, South America, North America, all together in Pangea. Now it's separated into Laurasia it said Laurasia / Gondwana land, then just Laurasia. You see the subcontinent of India shooting up, smashing in, and now we get to the modern world. It's a pretty cool depiction, isn't it? How do they know all that stuff? Tell me, how do they know all that stuff? Looking at old rocks and looking at the magnetic fields that are trapped in those rocks. So there's obviously a faith factor, a faith that we are interpreting the data correctly, that the dating methods are correct, and so on. But that's the best scientific reproduction of how the Earth has had its surface change over time. And you notice a lot of time there's a lot less surface, continental surface than there is today. Could that be related to global temperatures? We know that we are still in a cooler than average, actually, I think we're right about average temperature for the Earth now. We've been in a cold stage. We're recovering from the ice age. So, maybe we'll sometime end up back like that. So talking about the magnetic fields, the Earth has a planet-wide magnetic field. The reason for this planet-wide magnetic field is not because we have a big bar magnet there in the center of the Earth. It sounds fun, but it just wouldn't make any sense. So what we believe is going on is that there is a magnetic dynamo in the Earth. Remember, the Earth, the outermost layer is the crust. Then you have the mantle, and then inside the mantle is the liquid core. Well, we know from physics that if you have ionized or charged or conducting material that is swirling around and you have convection, that will create a magnetic field. And so it's believed that that's what's going on in that liquid core. We have stuff swirling around, iron and nickel, which is conducting, and we have convection, that is hot material is floating up, cold material sinking. And together that creates the Earth's magnetic field. And we saw previously, we talked about it on Friday, that we have magnetic field reversals that occur like roughly every 200,000 years. But it's been almost 1 million years since the last one, if we're interpreting the data right. So we're way overdue. The Earth isn't the only thing with magnetic fields. This gives us something to reference when we look at other objects and their magnetic fields. The sun is a great object to study when it comes to magnetic fields. The sun has very strong magnetic fields, and the sun's magnetic fields flip much more often than the Earth's. They flip on average about, I think it's about every 11 years. I, of course, failed to look up what the timing is for the sun here, but it flips a lot. And so we can study what's going on with the flipping. And scientists think they have a reasonably good understanding. It has to do with the storms going on with the sun. Well, right now there's something really bizarre going on with the sun. Has anybody read about that? The sun is becoming less active. It's having less storms. And when the sun has less storms, we receive less energy from the sun. If we receive less energy from the sun, what's going to happen to us? We should get colder. Furthermore, I was reading an article this week, and I'm not sure how reliable the guy was, but he was saying that also when the sun is less active, we actually receive more solar wind, that is charged particles coming from the sun, which causes the Earth to have more reflected clouds. A higher albedo is the term for the reflectivity. So we reflect more light, and that will once again make us cool. So the conditions right now are suggesting that the Earth should be going into a cooling stage. What evidence do we have for this? The number of storms in the sun has dropped, and with that, the time between magnetic field reversals has extended. So we know that the sun is doing something unique. So in your lifetime, you will know for sure if humans are causing this global warming or if it is all part of the sun. Because if we start cooling within the next couple decades, guys, if the sun goes dormant, if the sun doesn't go dormant, of course, this is off the table. But if the sun goes dormant, we should be cooling within the next couple decades. If we don't cool within the next couple decades, then we'll know for sure, yeah, this is man-made. Because nature says that we should start cooling now. If we don't start cooling, nature said we should be warming. But now nature's saying we should go to the cooling stage. So it's kind of good that what is right now a huge political hot potato in the science arena We can say there's a good chance that it will be absolutely so. There will be no deniers on either side. They'll all just say it's this if we go into that cooling stage. Oh, I should have mentioned, the Earth's magnetic field is important to us. It's important to us because it deflects that solar wind. The charged particles that come from the sun are deflected so they protect us. If we don't have a magnetic field, we'll get a lot more radiation. Now, you know I don't believe that life on Earth evolved. But if I did, I would say that it should have been a punctuated evolution. That is, you have things go on without much change and all of a sudden a lot of change. Because when you have magnetic field reversals, then you have a lot more charged particles coming through the bodies of the living things, causing mutations. If you have a lot more mutations, you're more likely to have more change. So the magnetic field does a lot to protect us. Atmosphere. The Earth obviously has an atmosphere. We breathe it. The composition of the atmosphere is roughly 79% nitrogen gas. That's N2. Nitrogen bonded to nitrogen, diatomic molecule. About 21% oxygen gas. Oxygen bound to oxygen, another diatomic gas. What does that leave? Virtually nothing else. It's almost exclusively those two. So the mass of the atmosphere is about 1/1,000,000th of the mass of the Earth. So it's really unimportant when you talk about the mass of the Earth. But it's really important to us because it's what we breathe. The atmosphere, if you look at pictures, sometimes you can see a little bit on the edge, but it's so thin compared to the size of the Earth that it's thinner than the apple's skin is compared to the size of the apple. Right? So our atmosphere is a really minor thing, but it's important. The hydrosphere is the water that covers the Earth. So we're going to talk about those two things next. The atmosphere and the hydrosphere. So first, the atmosphere. We have atmospheric pressure. How do I know there's atmospheric pressure? Well, you can't discern it really because you're just used to it. But you do know that when you get in water, the water is pushing on you harder than the air was. So that if you dive down, you start to feel it in your sinuses. And the same works if you're driving your car and you go up in the mountains, you start feeling it. That's because the pressure is different. Your body's trying to respond to it. You don't feel it on your skin, even though it's there, but you feel the difference caused. And it's because the air pressure is the result of the weight of all of the air above you. Right? There's a lot of air above us. Now, if I go to my house in Colorado, not nearly as much air above me. I think atmospheric pressure is like 70% there what it is here. So it's a much lower pressure. Can I tell the difference? Well, I can if I exercise. If I exercise, I get winded a lot quicker. Why? Because there's less air pressure, which means I'm not getting as much oxygen in my lungs, which means, I get winded easier. So we call the atmospheric pressure at sea level 1 atmosphere. So 1 atmosphere is actually defined as a number, I think it's 14.7 pounds per square inch, or 760 millimeters of mercury, for those who care about, it's also called a torr, or 1.013, it's 100, 1.013 times 10 to the 5th newtons per meter squared. That's the metric measurement. But that's atmospheric pressure. You go up there to higher elevation, it drops because there's less air above you. Here is a breakdown of the atmosphere going from the Earth up. So the lowest level, the level that we live in, is the troposphere. And what's interesting to me is looking at the temperature variation. The temperatures get colder as you go up higher. Makes sense? I'll have you know, one of my former students has hiked Mount Everest, not once, but twice, trying to do it without supplemental oxygen. The first time he summited without oxygen, but he had to take oxygen on the way down. The second time, I think he did the whole thing without supplemental oxygen. For the record, I think that's foolhardy.
Yeah.
They have the region up there at the top that they call the kill zone, right? Or dead zone.
Yeah.
Because humans cannot live there. You're just slowly dying when you're in that region. And going without oxygen is just speeding up the process. But so no one can live up there because there's just not enough oxygen. Your tissues are going to be dying, and it's really cold. And when you're so hypoxic, you probably aren't very aware of what's going on. So you get up here and you get to I think it's called the tropopause, where the temperature stops cooling. And now you're in the stratosphere. So stratosphere, we tend to think of stratosphere as the way up there. Well, if you look here, you say, well, that's just the lowest level that's not the troposphere. And the stratosphere, we have the opposite. As you go up, the temperature increases again. And notice ozone is here in the stratosphere. You get up to the top of the stratosphere, and it changes back again. You get into the it's funny, I don't have the name here. I'm sure there's a different name here. I don't remember it either. The uppermost layer is the ionosphere. I feel silly not having it there. Maybe. Well, depending on what you look at, you'll see there's a lot of subdivisions. There's got to be a subdivision for where it changes direction. The ionosphere is the highest region. The gases are ionized. That means that you have taken electrons off of the atoms. How does that happen? Well, you had collisions that knocked an electron through. And so that ionosphere is ionized gas. If you are into like ham radio, a lot of ham radio operators will try to use the ionosphere to get skips. Their electromagnetic waves will go up and hit that ionized region, which acts as a reflector for their waves, and so they can reflect and hit the other side of the Earth. That's where the auroras are. Aurora borealis, otherwise known as northern lights. Aurora australis, otherwise known as southern lights. Those occur up there in the ionosphere. So the air, or the height here, goes up to around 140-ish kilometers above the surface of the Earth. By that point, the atmosphere is so thin, we say you've escaped Earth's atmosphere. So how high is the International Space Station? If we were to believe, well, it wasn't an International Space Station in our homework problem, was it? It just said a satellite. But we have a problem in homework in physics. They had satellites somewhere around 400 kilometers above the surface of the Earth. That's going to be well outside of the Earth's atmosphere. So the goal there is so it's flying free of any encumbrances from the atmosphere. Yeah, I forgot that I even have information about them here. I forgot that I had that written there. That's why I have this other slide to give us the last thing about the ionosphere. So, northern lights. Northern lights, or aurora, in general, are an interaction between the cosmic wind and the Earth's atmosphere. So the cosmic wind is charged particles coming from the sun. The sun, believe it or not, is losing mass at an incredible rate. But because the sun's mass is like 2 times 10 to the 30th kilograms, it don't care. The amount of mass that the sun loses is enormous compared to us, but it's minuscule compared to the sun. So it has this mass that's being blown away from it constantly. And so we constantly have this cloud of solar particles, the cosmic wind, that's striking the Earth. Now the Earth's atmosphere will deflect it. The Earth's atmosphere will deflect it because of, not the atmosphere, the magnetic field. So in this picture you see the particles coming, and if you had the Earth like this and the particles are coming like that, the Earth's magnetic field is going to make them go like this, splits them, and makes them go around the Earth. That's great. We're getting hit by less protons. Those protons going through our body could cause mutations and damage. But notice if you go to the north and south poles, instead of being split away, they start spiraling around magnetic field lines. Magnetic field lines are the way we talk about the force properties of the magnetic field. But we talk about them like the real lines coming out of the South Pole, or coming out of the North Pole of magnet going into the south, which leads to something else interesting there. If you look at that, You have the north on top, right? That's the North Pole. The magnetic field lines don't have arrows on them, but the magnetic field lines, yeah, let me change colors. They come out of the South Pole and go into the north. What that means is the North Pole is a south magnetic pole. The South Pole is the north magnetic pole. The reason for that is because they named them, kind of in ignorance, they said north-seeking pole of magnet. We call that the North Pole. North-seeking means it's going toward the North Geographic Pole. But magnets have opposites attract. So the north-seeking pole is seeking a south magnetic pole. And hence the reverse of the names. So anyway, if you're near the poles, those charged particles from the sun will spiral around the magnetic field lines and come on into the atmosphere. So if you're near the poles, you're not protected like you are when you are in the middle of the earth. I should also point out, if you're living at higher elevations, like my new home in Colorado, you're less protected as well. So you get more solar radiation there. Hence, there's a slight bigger risk of cancer because you're higher elevation. Anyway, those charged particles coming into the atmosphere then will excite electrons in molecules in the atmosphere. Excite those electrons to higher energy levels. What happens when you have an electron excited to a higher energy level? They fall back down, and they'll give off an energy equal to the difference. And so they're going to give off an emission spectrum. And that's what northern lights are. Northern lights are emission spectrum coming from the molecules in the upper atmosphere, in the ionosphere, because you have charged particles like protons passing by, exciting the electrons to higher energy levels. Now, as charged particles, the protons excite them, so you don't have an absorption spectrum there, because it wasn't light that excited them. But you have the emission spectrum and they fall back down. So that's what the northern lights are. So you have different colors in the northern lights. You can't see very well in the projector, but this region in here is green, as well as this region here. And then this region here is purple. And purple means that you have a different emission than you have from the green. So you can actually do some, hey, we've got this kind of gas here and this kind of gas here, if you can identify where the northern lights are coming from. Atmosphere, light, and global warming. First thing I want to point out is this picture here, I believe, is a picture of the ozone layer. That's what I think it is. There is no definition here, so I could be wrong, but we're going to go with it. Ozone. What is ozone? We have some people who take chemistry. What? Ozone is O3. It's a weird little molecule. It's a molecule that forms a triangle. And this ozone is actually really important to us. We don't like to breathe it. It makes our lungs burn. You can smell it. If you have like an electric drill and you pull it and you smell the smell it makes, that's ozone that's being created by the arcing. Well, that ozone is really important because that ozone will absorb ultraviolet radiation. Why is that important? Remember we talked about radiation and that's electromagnetic radiation. We have the really high energies were like gamma rays and ultraviolet. And then we have visible and infrared and radio. And we talked about energy because energy for the particle of light is Planck's constant times the frequency. High frequencies have higher energy. Higher energy means that it could be absorbed by molecules in our body and break bonds. That's bad. So we worry about high energy radiation. We don't worry so much about the low energy radiation. Ultraviolet radiation is high energy. But the ozone absorbs ultraviolet radiation. It absorbs the ultraviolet radiation, breaks the ring apart, and you form oxygen gas. So when it does its job, you're going to break down the ozone. But it's being naturally replenished, so ideally, we maintain this ozone up there that keeps protecting us from ultraviolet radiation. The problem is, we as humans like to use things like refrigerant. And Lord knows I love my air conditioner. Living out here in Nebraska, I don't think it's possible without an air conditioner. And what we like to use for refrigerants in our air conditioner are like methane that has had carbons replaced by halogens. So we have chlorofluorocarbons. And the problem with that is chlorofluorocarbons are what we call in chemistry a catalyst to the breaking down of ozone. What they do is they make it so it takes less energy to break ozone apart. Less energy means lower frequencies, like visible light, will break the ozone apart if they're in the presence of these chlorofluorocarbons. Well, there's a lot more visible light than there is ultraviolet light in the sunlight. And so if you have these there as a catalyst, you don't use it up. It just makes it so you can break the ozone apart easier. And so the ozone gets broken apart by visible light, and if you break up all of the ozone, then you have nothing to protect you from the ultraviolet light. So that's what the whole deal is with the ozone layer. It has nothing to do with temperatures on it, but it has everything to do with protecting us from ultraviolet radiation. Where are the problems most significant? They're most significant near the poles. So that's the ozone layer problem. Man clearly has a responsibility there. And we've done lots of things. It's, they can't manufacture air conditioning units that use the old refrigerants anymore. And it's really expensive to buy the old refrigerants these days, intentionally so, to try to keep people from using them. Then we have the greenhouse effect that we've talked about. Now, we've talked about the greenhouse effect, I think, a lot already. Is that accurate? Do you guys think you have an understanding of the greenhouse effect? Okay, simple questions with not simple answers. Is the greenhouse effect good? To a point, that's right. That's why I said not simple answers. To a point. What happens without the greenhouse effect? We become popsicles, we freeze. I swear I saw a commercial once where this company was somebody saying, I believe that we can create an Earth without a greenhouse effect. Well, that's not an Earth I can live in. I'm not for this company. We need the greenhouse effect. So what's the big deal then about the greenhouse effect? Too much of it is a bad thing. Too much of it, what's an example of too much greenhouse effect? Venus. Venus has too much greenhouse effect. The temperature is way too hot there. We could never live there. So we need the greenhouse effect to live, but we need it in the right amount. And so the greenhouse gases, like I said, water is the biggest one, but we talk about carbon dioxide because it's the one that we have a direct input on. That's the one that, because of the way our society has moved, we now do a lot of burning of stuff when we produce carbon dioxide. Now there's another one that nobody talks about that they really should. Methane gas. Why? Well, something that people like to do a lot, it turns out, is to eat beef. And when you're eating beef, you're doing way worse for the greenhouse effect than you could ever do by driving a Hummer. Because those cattle, I went to Washington State University, they did the seminal research measuring how much methane a cow produces through its flatulence and its belching. And the cattle produce enormous amounts of greenhouse gas. Furthermore, the deforestation that goes into producing more range for animals contributes to the cause. Chris Blake, who I'm sure you guys know, he said, I am a vegetarian not because of any health concerns or this or that, but because I actually believe that man is responsible in some way for global warming, and that is the single biggest thing we can do to combat global warming is to become a vegetarian. Which kind of points out a big flaw in the whole public to-do about global warming. People are willing to get all excited about the things that the big, bad, greedy companies are doing, but nobody's willing to change their diet to actually make a difference that would be much more meaningful. In fact, I read an article, and of course, I didn't do the calculations, that said if the entire Earth simply stopped eating meat, we would meet all of our greenhouse effect goals just with that move. Okay, so talked about that. Here is a map, or this is a picture that I like better that shows some chemistry ideas of what's going on. You have sunlight that comes in. If sunlight hits a cloud, it's reflected. Reflected, it doesn't come in, it doesn't warm us. So if the Earth has more clouds, has higher reflectivity, higher albedo, we would say, and it's going to cool off with more clouds, just naturally. Without the clouds, visible light gets in. The Earth absorbs that visible light. It emits light, but at a much lower temperature because the Earth's surface temperature is around 300 kelvins, whereas the sun's surface temperature is around 5,800 kelvins. Very different peak wavelength range. So the Earth is giving off primarily infrared radiation, whereas the sun's giving primarily visible light radiation. That infrared radiation is absorbed by the atmosphere. It doesn't get out very efficiently. And so a lot of the energy that comes up from the Earth is absorbed by the atmosphere. It stays in the Earth's atmosphere. There is a lot of infrared radiation coming from the sun. It gets absorbed in the atmosphere too and heats up the atmosphere too. So the absorbing of the infrared allows the energy to come into the Earth because it's being absorbed by the Earth, doesn't allow it to leave. And so that's the basis of the greenhouse effect. The Earth's temperature will just rise until the amount of energy leaving matches the amount coming in. The higher the temperature, the more radiation that is being produced, and hence you get a certain percentage that gets out, the more it gets out. All right, we're pretty much out of time. The last topic here is about the shaping of the Earth. The Earth's surface, we talked about the stages of planet formation. We had differentiation, cratering, flooding, and slow surface evolution. Slow surface evolution is what's going on today. Slow surface evolution on Earth is driven by fluid water and fluid air. Air is a fluid. It's not a liquid, it's a fluid. And as that covers the surface of the Earth, it will move things. You have erosion, which is breaking up material. When you are a bad person and you walk off the path over there at Holmes Lake, you break up the soil a little. That's erosion. Then you have weathering. Weathering is something that transports the eroded material to a new location. So when it rains, it'll weather, it'll run down. Or you can have a wind that would cause the same thing. And so we slowly have changing of the surface. So here's a picture of, I think it's the Grand Canyon, right? And you have lots of clear effects of the surface changing. Do we have impact craters you can see on the surface of the Earth? Yes. How many people have been to an impact crater you can see on the surface of the Earth? Which one have you been to?
There's one over in Russia that they have that is pretty cool.
Okay, so it's in Russia?
Yeah.
And do you know the name of it offhand?
No. I don't know the name, but I've been to one in Arizona, I believe.
Okay, I've been to that one. The Barringer Meteor Crater, sometimes just called Meteor Crater. It's outside of Flagstaff.
In the middle of that mining, like these.
Yes,
Yeah.
that's why it got the name Barringer. A steel magnate purchased the crater thinking that this is going to be a good place to mine iron. Well, the biggest rock they ever found was only about this big. But he spent a lot of money trying to mine it. We have some craters, but they've been quite weathered since then. They've been changed quite a bit. And so we don't have very many because they're around too long, they completely disappear. The Chicxulub crater on the Yucatan Peninsula, if I mispronounce these correctly, okay? I'm looking at you because you said you're from South America,
Yeah.
which I know Mexico is not, but you probably have some language skills I do not. So this Chicxulub crater wasn't even discovered until a few decades ago when people were looking for oil and they noticed some anomalies. And then they searched it and they found here's this big crater, mostly underwater, a little bit above water. It's been so changed by surface evolution you can't see it anymore. But they now believe that that is the key to what caused a mass extinction, the last mass extinction is called the fifth mass extinction, where a vast majority of all living species died because of a meteor impact there. On the moon, you see lots of craters. Why do we see lots of craters on the moon and only just a handful on the surface of the Earth?
Because the moon has black holes in it.
Yeah. There would be two logical conclusions. Either the moon just has a lot more impacts than we have, or the moon doesn't have something to change the surface. Both of those have some credence to them. Things that hit the moon, hit the moon. Things that hit the Earth often burn up in the atmosphere and don't hit the surface. But things that do hit the surface on the Earth, the surface will then reform, and over time you don't see them. Okay, I'm out of time by 2 minutes even, sorry. Have a great day. I'll see you in lab mañana. Remember to work on the homework.